welcome. This is the second day of the conference, and we are in room B, and this is the one devoted to topics ranging from statistics to machine learning. And today we have Federica Milinanni that will talk us about approximating feature information for efficient Markov chain Monte Carlo. And okay, so this is the first topic of the day, and we can go ahead since we are already ready to go.
Thank you for having me here today. And so I will start from the motivation to this problem of approximating this feature information. And the motivation comes from the field of Markov chain Monte Carlo methods for uncertainty quantification. And for a certain class of these methods, we need to compute the expected feature information matrix. And the models where I apply these MCMC methods are nonlinear ODEs models. And in this framework, the expected feature information requires the sensitivity matrix to be computed. So the main focus of my talk will be on the sensitivity matrix, and I will show a new method to approximate it that we call Pbsr algorithm. And we also proved an error analysis, and I will only show you the results of this error analysis together with some numerical results. Again. Okay. So the problem of approximating the feature information comes from the field of uncertainty quantification of parameters. In my case, in deterministic models, so ODE models, my models are about nerve cells, so reactions that happen in neurons. And to perform this uncertainty quantification, I use MCMC methods. Here is to give you an idea of the kind of models that I use, that are models of intracellular signaling pathways. So all the nodes here represent concentrations. They represent some compounds that are in the cells, like, for example, proteins, enzymes, or calcium ions. And all the arrows represent the reactions that lead from one compound to another. And I want to study the evolution in time of all the concentration of all these compounds. So I model them simply by an abstract vector x, that for me is a vector of concentration, and it's the state of the system. And I model it using this ODE, where the vector field f depends on x, the state, and of external inputs u that are set and controlled by the experimentalists, and on parameters p, that in my case are, for example, the reaction rate, the constant reaction rate, that are constant that describe how fast the reaction of these reactions happen. Then the experimentalists provide measurements, y, that in general are a function, g, of the states of the concentrations x, together with some parameters s for the readout. And these vectors of parameters, p and s, that together I will denote by theta, are unknown. And the purpose is to estimate these parameters theta using the experimental data that are provided by the experimentalists. And we don't want just a point estimate for these parameters, but we rather want to quantify the uncertainty that is in these parameters. And we want to do this by characterizing the posterior distribution. So here we can use the Bias Theorem that tells us that the posterior distribution can be expressed as a product of the likelihood times the prior distribution of parameters divided by a normalizing constant that, as you can see, is an integral in theta. And in my applications in systems biology, this parameter can be really high dimensional. So this integral is rather expensive to compute. That's why we rely on these Markov chain Monte Carlo methods. These methods are based on building a sequence of draws, theta 1, theta 2, and so on. And this sequence must be such that the next value of the chain, so theta k plus 1, is generated using a transition kernel Q that is dependent of the previous parameter of the chain, theta k. Moreover, we wanted the stationary distribution of this transition kernel Q is the posterior distribution, so the function that we want to characterize. And this means that after a transient of this chain, we will be sampling from this transition kernel as if we were sampling from the posterior distribution, which is really what we want to do. The most general method here is the Metropolis Hastings algorithm, where we generate a new proposal theta star for this chain, for the next value of the chain. And we generate it using this transition kernel Q, transition probability. And typically, this transition kernel is a random walk. And for example, we can assume it to be normally distributed and centered in the previous parameter of the chain, theta k. And then we can accept this proposal theta star. And so we set the next value theta k plus 1 as equal to theta star. Otherwise, we reject it. And we set the next value theta k plus 1 as equal to the previous value theta k. So we stay in the same value also for the next step. And this acceptance or rejection is done using this acceptance probability, alpha, that depends on the previous value, theta k, the proposal, theta star, and its expression contains this likelihood, prior, and random walk. However, as I told you before, we are working in high dimensions of the parameters. And when we use a random walk, we can have shortcomings of this Metropolis Hastings algorithm. And these are mainly related to low rates of acceptance. That means that this probability alpha is usually low, it's close to 0. So we often are in this case, in the second case, where we reject the new value. So we are always in the same area of the parameter space. But this is not good for an MCMC method, because we would like to explore the whole parameter space so that we can characterize, we can understand the behavior of the posterior distribution. And maybe just staying in a certain area of the parameter space, it means that we are maybe only in a mode of the posterior distribution, so we cannot realize that there are other modes in this distribution. And also related to this difficulty of exploring the whole parameter space, we have a poor mixing of the chain and highly correlated samples. That is not good if we want to characterize the posterior distribution. So what we can do is using a modification of this algorithm, that is the Metropolis adjusted Langevin algorithm, abbreviated as MALA. Here we consider the Langevin stochastic differential equation, where, as you can see, we have this drift term, that is the gradient in theta of this log posterior distribution. And this means that this process for theta will lead theta towards regions of higher posterior probability. And in regions of higher posterior probability, the acceptance probability is higher. So we avoid this problem of rejecting a lot of samples. Okay. Here, by discretizing this SDE using a first order Euler, we get the proposal mechanism, and then again we accept or reject using the same Metropolis acceptance probability as before. However, you can see here, this should be red, but I think you cannot see it. This term is an isotropic diffusion. So we are moving in the parameter space using an Euclidean geometry. But actually, the real geometry of the parameter space is, in general, not Euclidean, because this parameter theta can be strongly correlated, or they can show widely different variances. So this is if we consider the space according to the posterior probability, the space is like stretched in certain directions. So if we move with this isotropic rule, we are not adapting to the real geometry, the proper geometry of the space. And this can lead to an inefficient method, to inefficient moves in the parameter space that can also reduce the acceptance probability and bring the problems that I told you before. So the solution is to reconsider the Mala algorithm on a new geometry, so on a Riemann manifold. And this leads to this modification, Riemann manifold Mala, RMala, where we can use the metric tensor that characterize this Riemann manifold. And here we can redefine both the drift term using this G, the metric tensor, and also the Brownian motion. Okay, here. Of course, you see that this is a pretty complicated expression, but we can make some assumption and get rid of this term that again is red, but you cannot see it. Here you see that we have this derivative in theta. So if we assume that G is locally flat, then all this term disappears. So we eliminate this term, we simplify this expression, so we get to the simplified manifold Mala, SM Mala. And this is the method that we use to perform uncertainty quantification. And so again here, using this transition mechanism, we accept again with the Metropolis acceptance probability. So now we get to the question, what metric tensor to use. And as I was saying before, the parameterized density function space has an intrinsic geometry as a natural metric, and this metric is given by the expected feature information. So we gain the information from data, and we can reshape the space according to it. Here, by definition of this expected feature information, we have that G, the expected feature information, is a positive definite matrix, so we can use it as a position-specific metric for our Riemann manifold. As I was saying before, the models that I consider are nonlinear ODE models, so I will only restrict my analysis of computing the feature information in this case of nonlinear ODE models. So just for a bit of notation, I will denote by x the vector of states, and it is of dimension nx. F is the vector field of the ODE, and it depends on x and on the external inputs u in nu, and on parameters, the unknown parameters that we want to estimate, that are again in dimension np. Then here we make a simplification with respect to the first ODE system that I showed you, where we assume that the observations are direct measurements of the states. So we simply let y, the observation, be equal to the states plus an uncorrelated Gaussian noise, where we assume to know the variances here. So here the only parameters that we have to approximate is this vector p. So I will no longer denote the vector as theta, but only p. So p is our parameter that we want to estimate. Okay, so if we assume to have experimental measurements at times t1 to tn, and if we perform all the analytic computations for the expected information matrix, we get to this formula that in the end is pretty simple. We only need these variances, and we assume to know them. That are the variances of the measurement errors. And then this capital S, that is a matrix in nx times np dimension, and it is the sensitivity matrix of the ODE model. That is that its entries are the derivatives with respect to p of the states x. So if we can compute this S, we can define the metric tensor G. So we can implement our SM Mala method and perform uncertainty quantification. So now we wonder, how can we compute S numerically? And actually there is a very used method. This is the most used method for this purpose. That is forward sensitivity. That is based on this observation. If we derive in time the definition of the sensitivity matrix, we get to this ODE for the sensitivity matrix. And forward sensitivity method is based on solving at the same time the ODE in S and the ODE in X altogether. So the whole problem has dimension nx times p plus nx. That is pretty large considering this product nx times np. So it can be impractical also because we need to compute this sensitivity matrix here for all the time steps at which we have measurements, but this is only for one step in the Markov chain Monte Carlo method. So if we want to build a chain, we need to compute the sensitivity matrix many times. That's why we are looking for a more efficient method, and this is the question that we ask in our research group. And we start by considering again the same ODE for S, and we observe that this is a pretty simple ODE. It's just a first-order linear ODE system. But there is a small complicancy, that is that the matrix of coefficient, that is the gradient of the vector field f with respect to x, and the forcing term, the gradient in P, are non-constant. And I will, for simplicity, denote them by simply A and B. So we need to make some more effort to solve it. Then we realize that we want to compute the sensitivity at on a sequence of time steps, t0 to tk. So the idea is to define k ODE problems in an iterative fashion. So we use always the same ODE, and then we change the initial conditions. So we start with initial conditions at time t0. We use this ODE to compute the solution at time t1, and then we plug this solution as initial condition. But first, let's consider the easier case, where we have constant matrices A and B. And here we can rely on a pretty well-known result, this theorem that tells us that if the matrix A is invertible, then we can express the sensitivity matrix with this exact formula, where we have this exponential matrix e to the power t minus tk times A. And we can use this theorem, of course, in the case where our matrices of coefficient, the gradient of f in x, and the forcing term, the gradient in B, are constant. And this happens, for instance, when our solution is at equilibrium. And therefore, we can use, again, this formula, but adapted with all our terms. And here, again, we have this exponential matrix, e to the power delta tk times gradient of f in x. So I tried to focus your attention on these exponential matrices because they are the state transition matrices associated to the coefficient matrix. And more in general, these state transition matrices are related to a first-order homogeneous system, linear ODE system, where here the state transition matrix phi associated to the matrix A is the function, matrix valued functions, that let us represent the solution of this system at time t as the product of the state transition matrix times the initial condition. And here the state transition matrix has two entries. The first one is the time at which we want to compute the solution, and the second one is the time of the initial condition. So I introduced this state transition matrix because we will use it to deal with the general case when we have time variant matrices A and B. Here we use a bit more complicated theorem that, again, under some assumptions of continuity of the objects involved, we get another expression of the sensitivity matrix of the solution of this ODE system. And here you see that it appears the state transition matrix. But so far I only told you what the transition matrix is, its definition, but I didn't. What's happening?
Actually, all the times that you people arrive at the same.
Yeah. So to compute it effectively, we can use this result from control theory, that is the Peano-Beger series. So here the state transition matrix is given by this series, where all these summands I are given by this recursive formula, that is an integral of the coefficient matrix times the previous term of this series. And if you perform the computations with a constant matrix, you get the exponential matrix that we saw before. So the results are in accordance. So the constant case, of course, is a particular case of the general one. So if we have a constant coefficient matrix, then the state transition matrix is the exponential matrix. But of course, we need to consider it more generally. So we need to use this formula for S, for the solution of the sensitivity matrix, and this Peano-Beger series with all these integrals for the summands. And the idea is to approximate the integrals using the trapezoidal rule and truncate the Peano-Beger series. And this will lead to the method that we called the Peano-Beger series algorithm, or PBS abbreviated, where we assume first to have computed already the solutions of the nonlinear ODE problem, that it's an easier problem because its dimension is only nx, while the dimension of the sensitivity is nx times np. So this is not a problem to compute them. Then we plug the solutions, the approximated solutions, into the expressions for the gradients to compute the approximations of the gradients, both in x and in p. And then we use these approximations of the gradients to approximate the summands of the series using a trapezoidal rule. And then we sum all these summands to define the transition matrix, but we truncate at n equals to 2. Then we have another integral to approximate, again by trapezoidal rule. And finally, we can compute the sensitivity matrix at time step k plus 1, given the initial condition at time step tk. So this was a PBS algorithm. And we also performed an error analysis where, assuming some continuity conditions that are pretty common if you consider, for example, a function in C3. So these are just subcontinuity assumptions, don't look at them. And then assuming that the solution of the nonlinear ODE system has an error that is smaller than delta t3 to the power delta t to the power 3. Assuming these assumptions and also assuming a certain regularity of the time grid, we get that the global error in the sensitivity matrix scales quadratically in time in the largest time step size. So we implemented this method in Julia, but we made a bit small modifications. So here we need to first solve the ODE, the nonlinear ODE, and here we use the packages, differential equations, and Sondials. And this ODE solvers returns the solution at an adaptive time grid, T0, Tk. Then we check if the gradients in all the time steps, so at each of the time steps, we check if the gradient is approximately constant. If it's approximately constant, then we can rely on the first theorem that I showed you, the one with constant matrices. So we use the exponential transition matrix instead of considering all the series and truncating and approximating the integrals. Otherwise, if the gradients are not close to be constant, we use the PBS algorithm. However, we realized that the time steps could be too coarse, and therefore all this approximation were not good. We're providing a very inaccurate solution. So we thought about refining every intervals, time intervals. And since we didn't want to rerun the ODE solver, because it's in the end also is expensive if we perform it on all the time steps, then we simply interpolate the solution linearly, and then we perform the Pbsr algorithm on each of these refinements. And we call this whole method Pbsr algorithm, where R stands for refinement. So here, keep in mind that we have this if statement. So if the gradients are constant, we use always the exponential matrix, otherwise this PBS with refinement. But this refinement is increasing the computational time, so it could be a bit inefficient. So we thought also to implement another method where we always use this exponential transition matrix, even if the gradients are not close to constant. And this is what we call exponential algorithm. So now a last section about numerical results. So we applied both these algorithms to compute the approximations of the sensitivity matrix of two models of molecular signaling pathways that we call PKA and ChemKinase models, that are these systems biology models. We applied them also to a random linear system and to a two-way dynamical system that converges to a limit cycle. And to evaluate the accuracy, we compare this sensitivity matrices approximation with the forward sensitivity method that we consider as our reference, because its problem is not the accuracy but the inefficiency. And so we computed the relative errors at each time step k. So here we have some plots. Here are the results for the PKA model, that is a system of dimension 11 for the state space and 35 for the parameter space. Here on the x-axis you have the time step, and we're plotting the relative error that I was talking about. So relative error of the sensitivity with respect to the forward sensitivity method. The dashed line here is the solution provided by the exponential algorithm. So when we always use the exponential transition matrix. And the solid line is the solution from the Pbsr algorithm. And here, the circles denote the time steps at which the if statement is fulfilled, and so we are using the exponential transition matrix. And as you can see, of course, here we have an improvement of 1 to 2 order of magnitude. Here it's in log scale, which is pretty good for our applications. These are the results for the ChemKinase model, where we are increasing the dimensions. So we have 21 and 59 for the states and the parameter space. And also here we have an improvement of 1 to 2 orders of magnitude. And of course, we are not only interested in accuracy, but also on the timing result, on the efficiency. So we computed an average runtime. And the exponential algorithm, as we were expecting, is the fastest one. While for the other two methods, in the PKA model, that is a rather small model, we have that the two methods, Pbsr and forward sensitivity, have approximately the same average runtime. While when we increase the dimensions in the ChemKinase model here, we see that the Pbsr algorithm is more than 10 times faster than the forward sensitivity. And this suggests that if we increase the dimensions of the problem, the Pbsr becomes more and more efficient with respect to the forward sensitivity. So we thought about designing a random linear system of dimension n, both for the state space and the parameter space, that is defined with these random matrices and random vectors that are uniformly distributed. And we apply here, again, the two algorithms, and we vary the value of the dimension n. And we considered value from 5 to 100. And these are the results, the timing results. And as you can see, for high dimensions, the forward sensitivity is much more efficient than the Peano-Becker series algorithm. But you see that the exponential algorithm is always really, really efficient. So here comes the question, why should we use the Pbsr instead of the exponential algorithm? And the answer is that in some cases it's better, especially when the solution of the nonlinear ODE shows drastic variations in time. So these gradients of f are really non-constant. And this happens, for example, in the case of limit cycles, when the solution does never converge to a steady state, to an equilibrium point. And to show this, we performed again the computations, the simulations on this Chua circuit dynamical system that is pretty small, but it converges to a limit cycle. And here again, we see an improvement in the accuracy thanks to the Peano-Baker series algorithm. So in conclusion, we developed an alternative method to the forward sensitivity that is based on this Peano-Baker series. And this Peano-Baker series refined algorithm is more efficient than the forward sensitivity, but the exponential algorithm is even more efficient but less accurate. So what we recommend is to use forward sensitivity if we want an accurate approximation, exponential algorithm when we want an efficient algorithm, and the Pbsr if we want a trade-off. Now we come back to the motivation of this talk, that is using the approximation of the sensitivity to perform the SML algorithm. And we implemented the exponential algorithm and the forward sensitivity algorithm in C, and we applied them to this SML algorithm for sampling from the posterior distribution. And the result was that we sampled from the posterior distribution approximately 100 times faster. So it means that instead of taking 100 days, we take only 1 day to perform the computations. And the use of the exponential algorithm was, in a sense, justified because the system where we applied it, it was close to a steady state. So the gradients were approximately constant. And the next step will be to apply this Pbsr algorithm or on more general examples. We expect that it will improve the situation. So if you want to read more about the Peano-Baker series from a more analytical point of view, you can look at this paper. For the SMALA and RMALA algorithm, you can read this Girolami and Calderhead paper. And while for this method that I presented, we have recently submitted a paper on arXiv that you can find there. And also for this project, Olivia Eriksson, Andre Kramer, and Pierre Nyquist took part, so thank them. And thank you for the attention.
Are there any questions? Laura, you go.
Okay, thank you for the nice presentation. It was super clear. I have just a curiosity actually. Why did you use Julia? Because for efficiency reasons, for its easiness. Because I'm very interested in learning Julia, but it's a thing that I continue to like postpone. So I'm seeking for motivation actually.
No, the truth is that my supervisor didn't know how to code in Julia, and I had never worked in Julia, only MATLAB, Python, Java, C++, and so we said, okay, we can try with this new method that we were studying. So this was the reason to learn a new language. The first steps are a bit weird, but then you get used to it. And also we were interested in it because the scientific community is using more and more this programming language. And also it has some functionality if you learn how to use it. I'm still pretty new to them. They should get this language very fast. So you can improve really the timing of your code. Oh, welcome.
So you said the Peano-Baker series, right? So why did you choose two? And Can you try like
Yeah.
what's the number?
In the paper, there is the full explanation, but I will try to sum it up here. So coming back. Okay, here we are approximating these summands using the trapezoidal rule, and this gives at each time step delta t cube error. And when we here, if we consider the exact terms, when we truncate at n equals to 2, we get again a delta t cube error. So if we included a fourth term here, it would be an error of delta t4, but this would dominate. So we could include another term here if we approximated the integrals with a higher order integration rule.
So of course you took into account this truncation when you compute the
Yeah. Yeah, all the error analysis is like 10 pages in the paper if you want to go there.
Okay, so any other question from you?
Yeah.
But if I'm not mistaken, the problem is that you're actually introducing a metric on the space of parameters, and you're studying the evolution of them. It's a very beginning of the talk you did that. And you say that the Fisher information is the natural one in using the metric. But there are other metrics, and why the Fisher matrix is the one naturally analyzing for that?
Because the posterior distribution describes how the parameters are distributed using the information in the data. And this is exactly what the Fisher information tells you.
Okay, perfect.
So they are kind of related.
And another question that I have is this one. And in the end, you are estimating some parameters, and that's for sure.
Yeah.
It is possible to actually do the reverse problem. You start from a couple of or a plethora of parameters that are optimal, and you want to find the matrix that actually allows you to find this one as optimal. Is this problem studied? Is the reverse? You are not fixing the metric, you are fixing the optimal set of parameters, and you want to find the matrix that allows you to do that.
I don't understand the problem.
No.
So it's not
like that. It's the reverse problem. You are here and you fix the metric to use during the computation. And you find a couple of parameters. The problem is the reverse. If I give you a couple of parameters that I want to be optimal, which is not the case, you start from the solution. There is a way to understand which is the metric. What is the matrix that will lead you to the solution?
I don't really know because the matrix is related to the observation.
Yeah, I thought so.
So the inverse problem here is not.
Because I was interested in this concept of modifying the space of parameters and introducing the matrix and studying the evolution. And it's like taking the plane to like go wherever you want in a natural way in this case. Okay, so perfect. That was for me. And if anyone else has any question, I think we
So you said this metric is using the information from data, right?
Yeah.
But is it also using the information from the prior?
No, the prior.
Informative prior.
We don't care really much about the prior from the theoretical point of view because any prior will get you to the convergence to the posterior distribution. So there's a kind of independence between posteriors and prior. But here, in my okay, there are two situations that we are considering: either uniform priors or Gaussian priors, but always like centered in the parameter values that we think that are more suitable for the specific biological case.
The Fisher information metric for the posterior distribution.
Yeah.
can I one more?